In this question we're given the vectors A and B, and we're asked to find the vector product A cross B. Writing A as a column vector is 1, -1, -1. Writing B as a column vector, that's 1, 2, 1. Now we write the column vector ijk. We then write the first vector A, 1, -1, -1, followed by the second vector B, 1, 2, 1. We now make a copy of these three vectors. To work out A cross B, we're going to form three diagonals coming down. We're also going to form three diagonals coming up. We're going to find the products of the down diagonals, and we're going to subtract the products of the up diagonals. Set up two brackets separated by a minus. The products of the down diagonals we write in the first bracket, and the products of the up diagonals we write in the second bracket. I times -1 times 1 is minus I. We'll write the j term next. 1 times j times -1 is minus j, and the final diagonal is 1 times 2 times k, which is 2k. We subtract from this the product of the up diagonals. First of all, -1 times 2 times I is minus 2i. 1 times j times 1 is plus j. K times -1 times 1 is minus k. Simplifying this, we've got minus I, first bracket, minus 2i, which gives a plus 2i, so overall we've got I. Minus j in the first bracket, minus plus j in the second, which gives us minus 2j. And finally we've got plus 2k, then a minus k inside the brackets, which will give us a plus k. And this is the vector product A cross B, I minus 2j plus 3k. We have to find the equation of the line that passes through the points 1, 3, -2 and -1, 1, 3. So we call the points P and Q. So we're trying to find the equation of the line through P and Q. P is the point 1, 3, -2, Q is -1, 1, 3. To find the equation of a line, we need a point in the line. We can choose either P or Q. We'll choose P. We also need to find a direction vector for the line. Now, a direction vector for the line would be the vector PQ. PQ is given by Q minus P. Components of Q, -1, 1, 3, minus the components of P, 1, 3, -2, which gives -2, -2, 5 as our direction vector for the line. The equation of the line will be given by x minus 1, y minus 3, and z minus 2 on the top, and on the bottom we place our direction vector -2, -2, 5. This will then be the equation of the line in symmetric form. We're asked to give it in parametric form, so we set these equations equal to a parameter t, say. And then by rearranging, taking the minus 2 across and multiplying, minus 2t, taking the minus 1 across to give plus 1, we get our parametric equations. So the x will be negative 2t plus 1, negative 2 times t is negative 2t, plus 3 will be the y, and finally taking the 5 across is 5t minus 2 for our z. And these are the parametric equations for this line. So we're asked to find the equation of a plane. In order to do that, we need to know a normal vector to the plane and also a point on the plane. And that's exactly what we're given. The normal vector is 3i minus 2j minus 2k. The point is the point 2, negative 1, 3. If we call this point P, then the position vector of P will be the components 2, negative 1, 3. If we take a general point on the plane R, it will have x, y and z as its components. To work out the equation of the plane, we work out n dot r is equal to n dot p. So n in its component form is 3, negative 2, negative 2. R is x, y, z. Is equal to n, again 3, negative 2, negative 2, dotted with the point P, 2, negative 1, 3. Dotting the left hand side gives 3x minus 2y minus 2z. And dotting the right hand side gives us 6 plus 2 minus 6, which gives us the equation of the plane is 3x minus 2y minus 2z is equal to 2. We've got three matrices A, B and C. Part A, we're asked to work out 4a minus 3b plus c. So that's 4 times the matrix A, 5, negative 2, 3, 4, minus 3 times the matrix B, minus 3 times minus 2, P, minus 4, 3, plus the matrix C, plus 3, Q, 7, negative 2. First entry will be 4 5s are 20, minus 3 times minus 2 is plus 6, so that's 26, then plus 3, so the first entry is 29. 4 times negative 2 is negative 8, minus 3p, plus q. The third entry, 4 3s are 12, minus 3 times minus 4 is also 12, so that's 24, plus 7, which is 31. Final entry, 4 4s are 16, minus 3 times 3, so it's 16 minus 9, which is 7, minus 2, which gives us 5. Part B, we're asked to find the product AB. Matrix A, 5, negative 2, 3, 4, multiplied by the matrix B, negative 2, P, negative 4, 3. To get the first entry in the product, we take the first row times the first column. 5 times negative 2 is negative 10, minus 2 times minus 4 is plus 8, combining to give negative 2. First row in the second column, 5 times P is 5P, minus 2 times 3, 5P minus 6. Then the second row in the first column, 3 times negative 2 is negative 6, 4 times negative 4 is negative 16, negative 6 minus 16, negative 22. And finally, the second row on the second column, 3 times P, 3P, 4 times 3 is 12, 3P plus 12. We're asked to find the determinant of this matrix D. So we write down the matrix and then another copy of it. we'll draw 3 diagonals coming down the way, 3 diagonals coming up. We're going to find the product of the 3 down diagonals and take away the product of the 3 up diagonals, and that will give us the determinant of the matrix D, det D. Form 2 brackets separated by a minus. First bracket, we put the product of the 3 down diagonals. 1 times 1 times minus 2 is minus 2. 4 times minus 1 times 0 is 0. 3 times 2 times 2 is 12. Second bracket, the up diagonals, 0 times 1 times 3 is 0. 2 times minus 1 times 1 is minus 2. And minus 2 times 2 times 4 is minus 16. Result of the first bracket is negative 2 plus 12 is 10. The second bracket is negative 18. Because there's a minus outside the second bracket, that will become 10 plus 18. So det D is equal to 10 plus 18, 28. We're asked to find E inverse, the inverse of the 2 by 2 matrix E. First of all, we find the determinant of E. Now the determinant of E is the product 3 times 6 minus 2 times minus 1. So that is 18 minus 2 times minus 1 is plus 2, so that will give us 20. Det E is 20. The inverse of the matrix E is then given by 1 over 20 times the matrix E, swapping the 2 diagonals, the 3 and the 6, to give a 6 and a 3, and then the minus 1 changes its sign to become plus 1, and the 2 changes to become minus 2. So this is the inverse matrix, E inverse. We have to find the first 3 terms in the Maclaurin series for e to the 3x. First of all, f of x equals e to the 3x, so f of 0 is e to the 3 times 0, which is e to the 0, and that's just 1. Differentiating f of x to get f dashed x will be e to the 3x times 3, or 3e to the 3x. So the f dashed of 0 is 3 times e to the 0. 3 times 1, so f dashed of 0 is 3. F double dashed x, differentiating 3e to the 3x, will give us 3e to the 3x times 3, which is 9e to the 3x. F double dashed of 0 is then 9 times e to the 0, which is 9 times 1, so that's 9. Our Maclaurin series is given by f of x equals f of 0 plus f dash 0 times x plus f double dash 0 times x squared over 2 factorial. The first term in this is f of 0, which is just 1. Second term, f dash 0 is 3 times x, 3x, and then f double dashed of 0 is 9, 9 times x squared over 2 factorial. 2 factorial is just 2, so it's 9 over 2 times x squared. And this is our first 3 terms of the Maclaurin series for e to the 3x. So we're going to use this iterative formula with a starting value of x not equal to 2 to find a root lying between 1 and 2. What we'll do is we'll work to 4 decimal places and stop when 2 of the iterates are the same to 4 decimal places. Start off with a value of x not equals 2, so press 2 enter on our calculator. The iterative formula can then be entered on the calculator as in brackets 3 answers plus 4 taken to the power a quarter or 0.25. When we enter this, we get our first iterate x1 equal to 1.7783. Pressing enter again gives us a second iterate of 1.7479. We continue to do this and we find that our fifth iterate is 1.7430 and our sixth iterate is the same as this. Because these two values are the same, that means that we can now write down the root. And rounding to two decimal places, that would be 1.74. We do this using the integrating factor method. The integrating factor is given by e to the integral of what's multiplying the y here, which is 1 over x. So the integrating factor is e to the integral of 1 over x dx. Now the integral of 1 over x dx is log x. So this is e to the log x. E to the log x is just x. So the integrating factor is x. The solution is then given by the integrating factor times y is equal to the integral of the integrating factor times this right hand side dx. Integrating factor times y is equal to integrating factor times the original right hand side. So that's x times y is equal to the integral of x times 5x squared dx. So xy is equal to the integral of 5x cubed dx. Integrating 5x cubed is 5x to the 4 divided by 4, or 5 quarters x to the 4 plus c. So xy is equal to 5 quarters x to the 4 plus c. To then find what y is, we divide all through by x. So y is equal to 5 over 4x cubed plus c over x. And this is the general solution of the differential equation. To begin with, we try to show that this is true for n is equal to 1. Now, when n is equal to 1, on the left hand side, this is just the sum from r equals 1 to 1 of 8r, and that's just equal to 8, one single term. The right hand side, when n is equal to 1, 4n times n plus 1, that will be 4 times 1 times 1 plus 1, 4 times 2, which is 8 also. So the result is true for n equals 1. We now assume the result is true for n is equal to k. In other words, the sum r equals 1 to k of 8r is equal to 4k times k plus 1. In other words, the sum r equals 1 to k of 8r, now when we put r equals 1 in, we get 8. 8 times 1. When we put r equals 2 in, we get 16, which is 8 times 2. R equals 3, 8 times 3, all the way up to fitting k in is 8 times k. And from our assumption, this is equal to 4k bracket k plus 1. Now we want to show that this will then become true for a further term up, for the sum r equals 1 up to k plus 1. We want to show that this is going to be 4 times k plus 1 times k plus 1 plus 1. So if we add an extra term to each side, the extra term would be 8 times k plus 1, the next term up from this, to each side of this equation. Now, adding it to the left hand side, we've already got the sum up to 8 times k, plus this extra term 8 times k plus 1. Adding it to the right hand side, to the 4k bracket k plus 1, we get this. The left hand side is then just the sum r equals 1, not just to k, but to k plus 1 of 8r. The right hand side, we can multiply out these brackets. 4k times k is 4k squared, plus 4k times 1 plus 4k, and then plus 8k plus 8. We can simplify that, and that will give us 4k squared plus 12k plus 8. Common factor of 4, and we take that outside a set of brackets with k squared plus 3k plus 2 inside. We can factorise the k squared plus 3k plus 2. So that the sum r equals 1 to k plus 1 of 8r is 4, and factorising k squared plus 3k plus 2 is k plus 1 times k plus 2. K plus 2 can be written as k plus 1 plus 1. And when we do that, we see that the right hand side is then the same as the original, but with k plus 1 instead of the k. So what we've done is we've shown that the result is also true for n equals k plus 1 whenever it is true for n equals k. And since it's also true for n equals 1, then by the principle of induction it's true for all n, an element of natural numbers. Okay, we have to use the Euclidean algorithm to obtain the greatest common divisor, GCD, of 1696 and 1504. Now, the 1696, if we use our calculator and divide this by 1504, now we're getting an answer of 1.127 and so on. If we take the 1 away from this and then multiply the remaining bit, 0.1276, by 1504, we see that 1504 goes into 1696 once with a remainder of 192. So this 1696 is equal to 1 times 1504 plus 192. We now take the 1504 over to the left hand side and we divide the 1504 by the 192. We do that in our calculator. 1504 divided by 192. We see that it's 7.8333, so it goes 7 times. So we can write that it's equal to 7 times 192. Now to get the remainder, if we take the 7 away from the answer, we get 0.8333, and we times this by the divisor 192. This gives us a remainder of 160. We now take the 192 over to the left hand side and we divide 160 into the 192. 192 divide by 160, and we see that it goes 1.2 times. Take away the 1 and multiply the 0.2 by the 160. And we see that there's a remainder of 32. So 192 is 1 times 160 plus 32. We now take the 160 over to the left hand side and we divide by 32. This time we find it goes exactly. 160 is 5 times 32. When we use the Euclidean algorithm, when we reach this stage where there's no remainder, then the number in this position then gives us what we're after, the GCD. So the greatest common divisor of 1696 and 1504 is equal to 32.